Hello, my name is Ouassim from the University of Ottawa, and today I'm going to present our work, ENDN and Enhanced NDN Architecture with the P4-programmable data plane. I will start by going over the motivation underlying our work, then I will present our proposed architecture and the different modules inside it. After that, I will show some experiments we did as a proof of concept. Finally, I will conclude and present some future work directions. First, let's start with the motivation. In the current internet, let's look at the example of a user who wants to access a video hosted in YouTube. When the user queries the video, it is forwarded to the YouTube application server, whose main objective is the content generation and hosting. However, the current network usually only offers best effort forwarding. So the YouTube server also needs to handle several content delivery tasks like congestion control, firewall, bitrate adjustment, and geofencing. Hence, most of the intelligence is in the application. The main question that our work tries to answer is, can we put these content delivery tasks inside the network instead of having them done by the application? More precisely, can we have more intelligence in the network? And so, we want to examine the idea of an application-centric network. Current networks like the internet usually only offer a single delivery service to the applications. As a result, providers have to configure the applications to adapt to the network. On the other hand, an application-centric network would be able to adapt to the specific requirements of the applications by allowing the specification of custom forwarding services. The providers would then configure the network to adapt to the application needs. The advantages of this approach are as follows. The optimization of available network resources to better serve the hosted application needs, a better network manageability by allowing every application forwarding logic to be configured in isolation in the network, and a faster resolution of network issues that can be detected and mitigated directly in the network where they happen. These advantages are especially prominent in the context of content provider networks like Netflix and Google, where the providers manage both the network and the applications hosted on it. Here are some existing solutions that can help us achieve an application-centric network. The first important solution is NDN. In NDN, the network is aware of the content shared by the applications, and so it can optimize the delivery of the contents to the requesters using, for example, caching. The second solution is network programmability. It allows providers to completely specify their custom forwarding behaviors directly in the network. One of the most prominent solutions that allows network programmability is SDN, which does programmability completely in the control plane. Another solution is P4, which is a programming language that allows the data plane to be programmed. However, these existing solutions face several challenges. For example, NDN is very well suited for applications that rely on pull traffic, but it faces challenges with other content delivery patterns, like for example the publish-subscribe or push patterns. On the other hand, current P4 data planes allow for a single large P4 program to run in the switch. This means that if providers need to add support for a new application forwarding logic, they need to update this large P4 program and then install it in the switch, which would need to be reset. Hence, downtime is always needed for updates. Additionally, P4 was designed in the context of IP, where the protocols have fixed size header fields. As a result, P4 has limitations when processing string-based protocols like NDN, which revolves around the variable length content name string. Consequently, while NDN and P4 allow us to move towards better support of application needs in the network layer, an application-centric network architecture is still missing. The main objective of our work is to design a novel network architecture that could be used to build an application-centric network. Our proposed architecture is an enhanced NDN architecture called ENDN that offers the following key features: an extensible catalog of network services that the applications can choose from, support for new content delivery patterns like the publish-subscribe or the push patterns, allow the programming of custom forwarding functions directly in the network layer. Finally, provide the means to configure these functions in the switches without incurring any downtime. The first feature is implemented at the level of the control plane, while the three others are offered by the data plane. Let's look at an overview of ENDN. In ENDN, the control plane offers an extensible catalog of network services to the applications. Examples of these services are content delivery patterns like the publish-subscribe pattern, or custom forwarding behaviors like congestion control, adaptive forwarding, or monitoring. The applications then specify their network flows to the control plane. A flow is specified by an NDN namespace along with the selected list of services that need to be applied to it. The control plane uses the different application requirements to generate the configuration of the data plane and then manage it. The technologies that we use in our data plane are NDN with some enhancements and P4. The control and data planes form together the ENDN architecture. However, the main focus of our paper is in the design of the programmable data plane. Hence, the network services are currently implemented as data plane configuration templates that are combined together. I will present you now the details of our proposed architecture. The data plane of ENDN has two main modules, EProcessing and forwarding logic. The EProcessing module contains the NDN forwarding pipeline with some modifications to support new content delivery patterns. Another modification we did to the NDN forwarding pipeline is to put the content store outside of the fast path. It is accessible through an internal phase to allow for easier control of caching decisions using next hops. The forwarding logic module contains several P4 functions that implement complex stateful forwarding behaviors per namespace, like for example, telemetering, geofencing, and stateful firewall. Hence, another goal of the EProcessing module is to associate namespaces to P4 functions, as well as prepare packets for P4. Let's see how the EProcessing module works in more details. The EProcessing module follows the normal NDN forwarding pipeline with the following modifications to the EPIT and EFIB tables. The first modification we do is to promote the EPIT as a routing table for data packets. This means that EPIT entries no longer necessarily represent a previously forwarded interest, but can be created proactively by the control plane. As the control plane can now create EPIT entries, we want some of these entries to be persistent. This means that they won't be deleted after a data packet is forwarded through them. Like in NDN, EPIT entries have an optional timer that is used as a form of garbage collection. Finally, both the EPIT and EFIB entries have an additional field that contains the name of the P4 function to execute. With these modifications, we call these forwarding tables EPIT and EFIB. The modifications I just described allow ENDN to support additional content delivery patterns. Publish-subscribe can be done by configuring the EFIB route to create persistent EPIT entries when interests are forwarded. Push can be done by inserting non-expiring persistent EPIT routes. Let's now look at an overview of the EProcessing module as a whole. When an NDN packet is received, it is first parsed to extract the values of the different header fields, the most important one being the content name. The parsing is done here and not in P4 because it involves a lot of string processing that P4 cannot do efficiently. The content name is then used in the forwarding pipeline to query the EFIB and EPIT tables and retrieve the extracted routes containing the possible next hops to use. These extracted routes, alongside the P4 function name to execute, are part of the E packet that also contains the parsed NDN packets. This E packet is then passed to the forwarding logic module for processing by a P4 function. Let's now see how the forwarding logic module processes E packets. When the E packet is received by the forwarding logic module, the P4 function target executing the requested function is retrieved. Every P4 function target runs isolated P4 code corresponding to a specific complex stateful forwarding behavior. Hence, every P4 function can be configured and modified at runtime without impacting the rest of the switch operation. The execution of the P4 function results in two outputs, a list of output actions and an optionally modified E packet. Here are some examples of output actions. A first action is to choose the next hops to which the packet will be forwarded among the list of possible next hops from the EFIB. Other actions are to drop the packets, notify the controller, modify some header fields, or execute some metering functionalities. Finally, if the E packet was modified, it will go through the deparser to modify the corresponding NDN packet accordingly. Let's now zoom inside the P4 function target. The P4 function target is a lightweight P4 code execution environment. It communicates with the rest of the forwarding pipeline using a standard metadata structure that is directly accessible from the P4 code. The standard metadata structure contains two sections. The input section contains simple fields filled by the forwarding logic module, like for example, the incoming phase of the packet. The output section contains several fields that tell the forwarding logic module which output action needs to be done, like for example, drop the packet. The P4 function target also implements external functions, which are functions accessible by the P4 code, but not coded in P4. Thus, external functions allow us to perform string processing efficiently. This is especially important to allow P4 to access and modify the data on the E packet. For example, an external function can hash a specified component of the content name and provide the hash integer value. This integer value can then be used in the P4 code to do a custom action based on the value of the hashed component. The P4 function target also manages stateful objects like registers and meters. Finally, as you can see here, the P4 code supported by the target contains only a match action pipeline. It contains no parser or deparser that are done outside of P4 because they rely on a lot of string processing. To better show the functionalities of ENDN, we implemented a proof of concept of ENDN and ran some experiments with it. Our proof of concept helped us validate the software feasibility of implementing ENDN. Our implementation is based on NFT that was modified to use some libraries from the P4 software switch BMV2 to implement the P4 function targets. Our experiments were then simulated using NDN sim. We also examined the hardware feasibility of an ENDN implementation and found that FPGA-based P4 hardware like the NetFPGA SUM card can be used where all the parts of the pipeline involving heavy string processing, like for example the EProcessing module or external functions, are done in HDL. The first experiment we ran is the scenario of a geofencing application. We have the following topology that contains two main consumer regions, consumers 1 and consumers 2. The consumers of every region can only access content specific to their region. This region-specific content is also cached in regional producers. In S1 and S2, we have a first P4 function that will tag the interest packets with their region of provenance. In SR1 and SR2, we have a P4 function that forwards the tagged interest to the regional producers until the traffic exceeds a predefined threshold. In this case, the excess traffic is offloaded to the central producers. The load of the central producers is balanced using a P4 function that acts as a round-robin load balancer. These are the results of the first experiments where we measured the average RTT of content retrieval per consumer region and for both NDN and ENDN. New consumers in every region start requesting data every 50 seconds, which increases their traffic progressively during the experiment. In NDN, geofencing is done at the level of the application, which means in the central producers. This incurs an additional delay. However, some consumers can still access content in their regional producers if they query the correct namespace, which explains the reduction of delay as consumers aware of the regional producers start requesting content. In that case, geofencing is managed by the available EFIB routes. In ENDN, as explained in the previous slide, geofencing is managed by the network. The regional producers are thus always used until the traffic is too important, which explains the low delay. The traffic is then offloaded to the central producers, which increases progressively the delay as the traffic increases. As a result, we can see that having more forwarding tasks managed directly by the network resulted in a reduction of delay in ENDN. The second experiment we ran is an application-aware congestion avoidance scenario. In this experiment, we have a topology that has two consumers and two producers running several applications with a link that can be congested in the middle. In switch 2, we put a P4 function that can detect congestions on the link, and in this case, it will send a new packet directly to the application running on producer 1 to notify it to decrease its bitrate. Here are the results we obtained when we measure the received throughput of every application. There are several applications running in the network. The sensor application has two namespaces, /sensor that corresponds to a publish-subscribe flow, and /sensor/alert that corresponds to a push flow. The VOD application is a normal pull application with two flows, one corresponding to the video search, while /VOD corresponds to the video streaming flow. At t = 100 seconds, a consumer starts streaming a video in the VOD application until t = 150 seconds, which causes a congestion. The network detects this congestion swiftly and notifies the producer of the sensor application to decrease its bitrate, as can be seen by the reduced received throughput of the /sensor traffic here. When the video streaming ends at t = 150 seconds, the network detects that the link is no longer congested and notifies the producer of the sensor application to increase its bitrate to the normal level. The congestion has then been avoided autonomously by the network. To conclude, the main contributions of our work are as follows. We designed ENDN, a new network architecture that can be used as the basis of an application-centric network. ENDN can offer an extensible catalog of network services to applications to allow for the configuration of complex stateful forwarding behaviors directly in the network layer. These services rely on new delivery patterns that are supported through modifications of the EPIT and EFIB tables of NDN, as well as programmability in the data plane using isolated P4 functions. As a future work, several challenges in the control plane can be examined, especially in terms of the northbound interface, consistency, and scalability. Finally, a study of the security implications of the new features introduced in NDN can be done to identify the potential vulnerabilities as well as the corresponding mitigation techniques. Thank you very much for your attention.